Great. I'm going to try and record this thing. If anybody has to leave early, that's fine. Feel free to do that. You can always watch the video. Did you all watch my video about the cube?
Yeah.
The submission of the cube? Did it make any sense?
Yes.
It's okay? So one of the problems in the review session packet, I didn't realize it, is the cube problem. How many ways are there to color a cube? So I may not go over that one here because you can watch the video of that. There are 20 problems in this review session packet. I don't think there's any chance I'll do them all. So I'm going to be jumping around, doing them out of order a little bit, kind of hitting different things. And for the things I don't hit, of course I have the solutions posted, you can read those. Or you can just come ask me about them some other time. I think it's a pretty good, I think this is really good. Like, in other words, if you really understand these 20 problems and then you go do the sample final, I mean, there's not going to be many holes in what you've looked at. It should be pretty comprehensive. I mean, I'm not going to swear that everything is covered in these pages, but a whole bunch of things are. So, careful, Peter. I'm recording back there.
Oh.
So thanks. Sorry. Let's see. I think I forgot to post the solutions to this homework that you're getting back today, but other than that, I think the website is pretty well up to date, ready to go. So we just have to kind of get ready for the test. I haven't really thought much about the exam yet. I mean, you know, there's the sample test, of course. I expect that the test will be a little bit heavier emphasis on the recent material. But the recent material, that means like 2 weeks worth of material. So even with more emphasis, it might only be 25 to 30% of the test, and then the other or whatever, 2/3 of the exam would be broken down into the first midterm and the second midterm. So I'm gonna have to look back over all of the sections. And we started off with the pigeonhole principle and applications of that, and then we moved into counting problems. So permutations, combinations, stars and bars, things of that nature. Inclusion, exclusion came into play. So you'll certainly be seeing a lot of those kinds of questions on the test. Then we did some stuff on the binomial theorem, combinatorial identities, combinatorial proofs, things of that nature, Pascal's formula. So you can take a look at that. That's kind of a chapter 5 or so. And then we jumped into recurrence relations and saw that was another strategy for how to count things to solve a smaller version of the same problem. So recurrence relations, and then the graph theory, all the stuff with you know, Eulerian trails and Hamilton cycles, Hamilton paths, bipartite graphs, isomorphic graphs, and crossing numbers of graphs, whether they're planar or not. That was the bulk of the stuff for the second exam. And then sort of since the second exam, as you know, the more recent material, chromatic number, chromatic polynomial, colorings of geometric figures using the Burnside theorem, that kind of thing. So that stuff should be maybe a little more fresh in mind. But it's a lot of stuff. You know, this is not a class where the material has been just building on itself all the time. We have been going in some different directions. And so what that means is that you do need to go back and refresh your memory more than you might. I mean, if you were taking Math 250B, for example, I would just say, oh, just study Chapter 7. You'll know it all. Because you have to know it all right at the end of the semester. This class is not like that. There's a bit of jumping around to different topics, kind of exploring a survey of combinatorics. So please do be sure to go back and look at everything. Does anyone have any questions? So, yeah, I'm gonna stay a while and work through as many of these as we can get through, and you know, at some point I may not get through all of them, and but I want to try and hit some of these while our minds are fresh and see how we do with them. Okay, I'm not going to go in order, but I'm just going to try and hit a variety of things on this review sheet. Okay, so there's no questions on any of the overview. That's a very quick overview, but you can look at the review packet. The review packets really for the exams to see more details. about the sorts of things you need to be able to do. Oh, one other thing, I may ask you to prove a theorem, something from class. Generally, if I'm asking you to prove something and I haven't told you in advance that I'm going to ask you specifically to prove it, it'll be something fairly short, probably a half a page or less, unless it's just something extraordinarily important. So Burnside's theorem would be in that category. I would not hesitate at all to ask you to prove that theorem. Another one might be the inclusion-exclusion formula. Again, something extremely important that we use a lot and that is reasonable to prove, even if you didn't just look at it 10 minutes before the test. But most of the things I would ask you to prove would be things that it'd be like, well, even if the person didn't study this, if they know the material, they can work it through. So that's. I don't like questions where it's sort of hit or miss. Either they studied it or they didn't, and it's either thumbs up or thumbs down on it. Those are not my favorite way to ask questions. If I have something like that, I would be more likely to give you a choice. Pick one of these three things to prove, and hopefully, if you didn't quite remember everything, maybe you remembered one of them. So I give you a choice on it. Anyway, focus on the big important results and the big important applications, things we've done a lot with. That's where your emphasis should really be. Not so much on little details that we didn't do much with. That make sense? Okay. Yeah, it's hard to give you an exact feeling for it, and I haven't thought about it, and I haven't written the test. But the only case where I would ask you something that was a proof that was fairly long would be if I focused on it a lot in class, and if it was something very important. Okay. You can ask me, as you're studying, you should be reading over my notes, you can ask me, is this something that would be reasonable to ask, that I might ask you, and then I'll tell you. Okay, so that's perfectly fine. All right, let's just dive in, see what we can do with some of these problems. I'm going to start with the first problem on the sheet. It's kind of an older problem, and here's what it says. We're going to have, it just says how many ways, and these questions are on the handout, so you don't have to necessarily copy them all down. How many ways are there to pick 8 balls from a large pile of identical red, white, and blue balls, okay, plus 1 pink, 1 lavender, and 1 tan ball. Okay. I didn't really specify here whether I'm keeping track of the order or not. So I want to come up with 8 balls, but I didn't say, if you pick 7 red balls and then a white ball, is that the same as grabbing a white ball and then 7 red balls? So that's where I have a note in the question to clarify that. Okay. You're welcome to ask for clarifications. I understand that the wording of these questions is critical to how to solve the problem. So I said in this question, I said note, order of selection does not matter. I will do my very, very best to make sure that there's no ambiguity in the statements that I asked. But if there is for any reason, you guys can certainly ask me about it. So I don't care what order they're selected in. It just means that I care which colors I have. That's all I care about. Which colors and how many of those colors. So what would you do to start off? Anybody have a suggestion? Okay, you want to use stars and bars? Okay. So order doesn't matter, and repetition is allowed. Of course, there's a little bit of a twist here. So repetition is sort of allowed. I'm allowed to repeat red balls, blue balls, or white balls, but I'm not allowed to repeat pink, lavender, or tan balls. So how do you incorporate stars and bars into a problem where there's some limitations involved? Sorry? Inclusion, exclusion, okay. Exactly. So there'll be some inclusion, exclusion here. So, Alex, I want to come back to you again real quick. So how do you want me to set up my stars and bars? And then we'll talk about where the inclusion, exclusion comes in.
I want to know how many of each I can choose. I'll say x1 plus x2 plus x3.
Well, there's red, white, and blue, plus pink, lavender, and tan.
So plus x4 plus 5, 6 equals 8.
Okay, so you have to grab a total of 8 balls, and those xi's are telling you how many of each. So x1 would be the number of red balls, and x2 might be the number of white balls, x3 would be the number of blue, and x4 would be the number of pink, x5 would be the number of lavender, I'm just abbreviating here, x6 would be the number of tan, right? So you have those classifications. And what other information can we build into this problem?
Restriction.
How do we write it, Peter?
The x4, x5, x6 must be less than equal to 1.
Okay, x4, x5, and x6 are less than or equal to 1. Exactly right. Okay. So what we can do, what we typically do when we're solving inequalities like this, is we first ignore the restrictions and we say if there were no limitations, how many solutions would there be? So if you'll recall, you can think of there being 6 bins, and you just put the balls in those bins, and in order to separate those bins, you have to have 5 dividers or bars, right? So this problem is going to have 5 bars, and at least the unrestricted problem, where you have no limitations, would have 8 stars. Okay, so without restrictions, we would get how many ways of selecting these balls? Good, 13 choose 5. Exactly. Okay. From that, we have to subtract violations. Okay, and the violations come in 3 different types here. You can violate the number of pink balls, the number of lavender balls, or the number of tan balls. And so it's good to create sets for each type of violation. Okay, and then that's where the inclusion exclusion is going to come in. So what I might do here is let capital A be the set of solutions with x4 at least 2. And then capital B would be the set of solutions with x5 being at least 2. And C would be the set of solutions with x6 being at least 2. Okay? So then from this 13 choose 5, what we're going to do is subtract the number of solutions that are in any of those sets. In other words, the union, right? So what we need to do, so the violations then, think about it in terms of violations, the number of violations is just the size of this union. And that's where the inclusion exclusion shows up, right? So for 3 sets, it's pretty simple. You just add up the sizes of those sets, then subtract the 2-way intersections, and then add the number of 3-way intersections, okay, which there's only 1. And now it's just a whole bunch of counting problems, okay? So first of all, notice A, B, and C are all going to be the same because they're symmetrical, because these are all 2's. So since they're all the same, they're all going to be, we can just multiply by 3 basically. So what is the size of set A? Well, in set A, you're saying I'm going to have at least 2 pink balls. So what you can do is imagine grabbing 2 pink balls and then starting the problem over again. If you grabbed 2 pink balls, then you only have 6 left to choose, right? And you can imagine now that you've grabbed 2 pink balls, there are no other restrictions now. So you freely can choose the remaining balls. So that would be, what would be the expression for the number of choices then for set A? Yeah, it's just 11 choose 5. By the way, what we're doing here is we're taking stars plus bars and we're choosing the bars. You could also choose the stars if you wanted. But I actually, the reason I like doing the bars actually is the number of bars is always the same. I don't have to figure it out more than once. Okay, so we have 3 times that. Then we're going to do minus. Now there's 3 intersections that are two-way. And again, because of the nature of these sets, there is symmetry about them. I can treat them all the same. So A intersect B. This would be solutions where there's at least 2 pink balls and at least 2 lavender balls. So I can go grab 2 of each of those types. So out of the 8 balls, we've already picked 4 of them. So I only have 4 more to pick. 4 stars and 5 bars, that would be 9 choose 5. Okay? And finally, 3-way intersections, we're going to have at least 2 of each kind of ball, so that's 6 balls already pre-chosen. That leaves me only 3 left to choose. So there's 3 stars, I'm sorry, only 2 left to choose. Because you were going to choose 8 balls, you've already chosen 6 of those. So you only have 2 balls left to choose, plus the 5 bars, so it's 7 choose 5. And that's what gets subtracted then from the total. So the final answer, don't forget, you've got to take the 13 choose 5 minus 3 times 11 choose 5 plus 3 times 9 choose 5 minus 7 choose 5. That would be the answer. Okay? Yeah, that's what I got. Can anybody think of another way that we could have done this problem?
Generating function?
Generating function, that's an interesting idea. So we'd be setting up 6 factors. 1 for the red, 1 for the white, 1 for the blue, 1 for the pink, 1 for the lavender, 1 for the tan. So for example, the red, you have an unlimited number of red. That isn't what I had in mind, by the way, but that's okay. So this would be the red term, and you'd have 3 terms that were like that. And then you'd have only 1 pink ball, so the number of pink balls that you could get would be either 0 or 1. And same thing for all of them. So you'd be looking for the coefficient of what in this expression? 8. Yeah, the coefficient of x to the 8th in this expansion. So of course this one is 1 over 1 minus x. So we'd be cubing that times 1 plus x cubed. So we actually would have 1 plus x over 1 minus x cubed. That would be the generating function for this problem. Okay. Finding the coefficient of x to the 8th, however, well, it would be tricky because there's 6 terms here, right? Yeah. So and using this closed form is actually not what you want to do. You would actually rather use this form of it to get there. So generating functions are great as long as the expression simplifies nicely so that you can easily read off the coefficients. This one really doesn't do that. So can anybody think of another approach? I mean, this is great. I'm glad you mentioned it because generating functions is a great way to describe these counting problems. It doesn't always work as a tool. I'm thinking of something just simpler than generating functions. Sort of more brute force, so to speak. Yeah, just do one case where you say, all right, I'm not going to use pink, lavender, or tan at all. Okay, so then you're going to choose 8 balls completely from the red, white, and blue. Right, so in that case you've got only 2 bars to separate the 3 colors of balls that you're going to work with, and you still need 8 stars. So you basically do one case where you use none of the special balls. Then you can just do a case where you use the pink ball only, but not the lavender and tan ball. another case where you use the lavender ball only, another one where you use the tan ball only, and then another case where you use both the pink and the lavender one, pink and tan, lavender and tan, and then one where you use all three. So you could actually go through all 8. I mean, I'm not saying this is better. It's always nice to think about other ways to do the problem. So you could have thought about 8 cases as in terms of what you chose of these special balls. And that tells you then how many of the red, white, and blue balls you need to supplement your choice with. So if you grab the pink, the lavender, and the tan ball, then you're only going to pick 5 balls out of the red, white, and blue ones. Okay? So if you did it that way, if you did these 8 cases like this, you would have no subtraction. Your final answer would just be 8 terms added together, and you would avoid inclusion exclusion. I'll let you guys try it. You can do it on your own later on. I mean, everybody has a calculator. You can figure out what this number is. Try it the direct approach. See if you get the same answer or something different. Make sense? Okay. It's really not that bad. It's not that bad. Okay. All right. I'm going to skip. I'm going to skip around a little bit. Okay, so let me go on to. I think I'll do problem 4. And we'll just depends how much time we need on these other problems. Maybe we'll come back to some of these that I'm skipping. Okay, so number 4. Okay, here's what it says. How many ways to distribute 6 objects to 5 boxes if, and there's going to be a few parts here, so a good chance to refresh our memory about this. So part A, both boxes and objects are labeled. What that means is that you can tell them apart. So you can tell the boxes apart and you can tell the objects apart. Does anybody have an idea what the answer is? Here's one choice. This would make a nice multiple choice problem. So Bora's voting for this one. Anybody want to vote for a different one? You know, it's important that you can think about these things correctly. It doesn't hurt to go back to the group work where we had the fire trucks going out to the fires, because that had a bunch of parts that were all kind of variations of the same column. This one is like that too. So are the objects making choices of boxes, or are the boxes making choices of objects, or what's the right way to think about this?
Each box has for each box you can choose one of the 6 objects.
So I have my 5 boxes, and because the boxes are labeled, I can actually sort of put them, write them down in order. So this is the first box, so it chooses.
It can choose any of the 6 boxes.
So it would have 6 choices. Okay, what about the second box? It would have to choose a different object, right? So that would be 5 choices. An object cannot be in 2 different boxes, right? So this box would only have 5 choices, because one of the objects is already here. So the second box would have to choose a different object. This box would have to choose a different object. So this would be another answer, which is not the same as this answer. Is it in my? Yeah. So it's basically doing a permutation here. That would be another choice. Anybody else want to chime in on this? So we look at the question, and does the question say that a box is limited to one object? So this first box, if we're saying it has 6 choices, I might argue with you and say, well, but it has lots more choices than that because it could choose multiple objects. And if it does that, then the second box would be limited and have less choices.
So I think it's the other way around.
Okay.
Objects have to choose to be put in a box.
Right, so each object has to go into a box. So the first object looks at the boxes and it has how many choices? 5. So then the second object comes along and it has how many choices? As long as the boxes can have more than one object in them, the second object still has 5 choices. Now, if I had some extra condition that said no box can have more than one object, then the second box would only have 4 choices. The second object would only have 4 choices, exactly, for which box it goes into. So, and in fact, you'd find out it would be impossible. If you had a condition that said a box cannot have more than one object in it, you're going to violate the pigeonhole principle. Right? You have more objects than boxes, so some box has to have at least 2 objects in it. Okay, so we're kind of coming around to this answer. This is what Hoyle had suggested. Each object has 5 choices of which box to go into, and those choices are all independent from each other. What you would want to say on the test, I don't just want an answer, you'd want to say something like, each object has 5 choices of boxes independent of other objects. So each object is making an independent choice of which box it's going to go into. I don't need a long essay, but I need some brief explanation. Okay, let's do a part B on this. Part B says the objects are unlabeled. That's just another way of saying that they are identical. Okay? And boxes are labeled. So you have 6 unlabeled objects and you have 5 labeled boxes. So what do you think? When the objects are all identical, stars and bars, right? Okay, good. And how many stars are you going to have? Right, 6 stars, those are the objects. And how many bars are you going to have? Good, 4 bars. Separate 5 boxes. So we can separate 5 boxes with 4 bars. So the answer is 10 choose 4. Very good, that's easy. Or 10 choose 6. Perfectly fine. All right, part C. Both objects and boxes are unlabeled. So I have 5 identical boxes and I have 6 identical objects. So I can't tell the boxes apart and I can't tell the objects apart. Good question? Yeah, it is a little tricky. So, and it's hard to draw any pictures because if you start drawing boxes like 1, 2, 3, 4, 5 like we drew before, then you're putting them in order again.
You can't tell the difference.
Yeah, all 6 objects have to be distributed into boxes, but I